Good afternoon, good morning, everybody, and welcome to today's VAMOS seminar. I have Dr. Tara Fortier with us today to give a talk. She received her PhD in physics from GILA and conducted her postdoctoral work as a director's fellow at Los Alamos National Laboratory. She's worked as a physicist in the time and frequency division at NIST, where her research has been focused on mode-locked lasers to extract timing signals from atomic clocks and facilitating comparisons between different types of atomic clocks as a means to test our current models of physics. Dr. Fortier actively serves as the broader optics and physics community as a fellow of Optical, as an executive board member of the APS Division of Laser Science, and as a science advisor to the White House NSF Q12 partnership. In addition to her work in physics, Dr. Fortier is committed to advancing and creating opportunities for women and underrepresented minorities in STEM. She currently serves on the executive board for the NIST Women in STEM group and is the chair of the International Conference on Lasers and Electro-Optics Task Force for Diversity and Inclusion. It's my pleasure to introduce her to talk to us today about her work in clocks at NIST. And I'll just remind everybody to please enter your questions in the Q&A here in Zoom, or if you're watching on YouTube, you can add them to the comment section there as well. So with that, Tara, please go ahead, and we're eager to listen to your talk today.
Thanks. I'm going to share my screen.
Yes, please.
Okay, let me know if you can see that.
Looks good.
And can you guys see my cursor?
Yes, we.
Okay. And to anyone who's out there, please feel free to interrupt and ask questions, because I get a little bit lost not being able to see people's faces and not know, whether people are there or not. Okay, so here you go. So yeah, thanks, Lindsay, for the introduction, and thanks for giving me the opportunity to be here and speak with you guys today. So as Lindsay mentioned, I'll be talking about atomic clocks and timing, as well as applications of atomic clocks. So I'm going to advance this slide. So I want to start by talking a little bit about the SI, because I work at NIST in the time and frequency division, and part of the mission of NIST, of course, is the development of standards and references, specifically with for the support of helping define the international system of units. And for those who don't know, the SI was redefined in 2018 to be based entirely on the unchanging fundamental properties of nature. So this SI is now, in some sense, fully quantum. And of course, if we're talking about atomic clocks, we're talking about time, and atomic clocks help to define the unit of the second. And what makes the second important in the SI units is the fact that it underpins the definition of 6 other units and is the most precisely defined of all those units. So if you look at the relative accuracies of the different units, we see that the second has an accuracy of about 10 to the minus 16, as well as the meter, which is defined through the second using the speed of light. So now the fundamental constants no longer have any uncertainty to them. They are now numbers. But if we look at the other units, say the kilogram or the ampere or the Kelvin, we see that they have much higher relative uncertainty. And time itself is interesting because it's so much better defined than those other units. And I hope to explain a little bit why that is as I go through the talk, kind of like as a kind of sideshow to this talk, but feel free to ask questions at any point. So I want to start by talking about how atomic clocks help in the definition of time, and as well as the definition of frequency. So they define both the SI second as well as the Hertz. And then from there, I want to move on to talk about how frequency combs are used to help synthesize electromagnetic signals from atomic references. That's really my area of specialty. So I work on building mode-locked lasers to help compare atomic clocks and to help distribute those atomic clock signals across the electromagnetic spectrum. And I'd like to conclude with, atomic clocks beyond timing. So how they can be used to test the fundamental physics, as well as in next generation applications. So let's begin with atomic clock basics. So I know that most of you are all AMO physicists, but I wanted to try to keep this, a little bit on the simpler side, because I was told that the audience would have grad students. So I'm sorry, you might hear my cat in the background. I'm gonna just let her sit beside me so she doesn't howl too much. So the nature of these times. Anyway, so okay, so why is it that we use atoms for timing? So one is that we're going to say hi, Lulu. One is that they make excellent frequency references. So in the end, we don't actually use atoms for time so much as we use them as frequency references. But if we want to think about them in terms of timing, when we think about systems that operate for timing, what we're often working with are periodic systems, such as pendulums, right, or the rotation of the Earth. And so here, the pendulum that we have actually is an electromagnetic wave. So that electromagnetic wave can be a photon with microwave energies or optical energies or even X-ray energies, if you're going to go to nuclear transitions in atoms. But the problem with, let's say something like a laser is that the frequency or the wavelengths out of a laser are not inherently stable. And so we need to stabilize the periodicity of that electromagnetic wave somehow. And so if we look at an atomic system, what atoms give us is, one, it's their naturally isolated system. So the internal forces to the atom are much, much, much stronger than the external forces. And what that does is it allows them to behave as closed systems that are very difficult to perturb from the outside. Another plus side of atoms is that they're identical and they're abundant, right? So if you create a ytterbium-171 atom here or on the other side of the universe, presumably the idea is they're identical, right? And they're abundant. And in addition to that, the transition frequencies are all very well defined and they're relatively well understood and can be controlled at parts in 10 to the minus 16 to parts in 10 to the minus 18. So that means that you can get up to 16 or 18 digits of resolution and frequency on an atomic transition by carefully preparing your atomic sample. Now, and specifically in some of the optical atomic clocks I'm going to speak about today, such as aluminum ion clock, the strontium lattice clock, and ytterbium lattice clock, these clocks operate on doubly forbidden or very weakly allowed hyperfine interactions. Transitions that are allowed by hyperfine interactions. And the idea with this is that they don't couple easily to other atomic transitions. And as a result, what you can have is you can have extremely long upper state lifetimes, greater than 1 second. Right? So what that gives us, if we have a very long upper state lifetime, we can have very narrow transition widths. And so with the idea with atomic clocks is to be able to produce the most pure state possible, you want to isolate the atoms. So you trap them in vacuum, you laser cool them, right? Then you trap them either in let's say with a RF fields or with optical in an optical lattice. And then in the end, you probe them. And the way that we actually feed back on the transition, as I said previously. So we have this electromagnetic wave itself that is not that stable. But what we do is we shine the light onto, this is all very loose talk. Just shine that light onto the atoms, right? If the light isn't resonant with the transition, it's basically the atomic sample is going to look transparent, right? And then when the laser is on resonance, what happens is the light is absorbed from the atom, and as a result, we get an absorption spectrum from that, and we can use that to feed back on the laser system to stabilize the periodicity in the electromagnetic wave. And as a result, what we end up having is laser light whose frequency is now highly stable and is coherent with the atomic transition. So in terms of atomic clocks, the atomic clocks that people are most familiar with, if they're familiar with atomic clocks at all, is the cesium fountain clock. And that is the clock that currently defines the SI second. So currently the SI second is actually defined as a certain number of oscillations of radiation in cesium. The transition frequency for the 133 cesium atom is around 9.192 gigahertz. So this clock operates with an accuracy of about 1 part in 10 to the 16, which gives you, if we translate that in terms of years, what would happen is you'd lose about 1 second over 350 million years, which seems excessive, but that's okay. At NIST and around the world, NMIs work to improve timing. So, we're losing 1 second every 350 million years is not good enough. So if you want to improve the accuracy of your clock, or if you want to improve, let's say your definition of the second, what you want to do is you want to go to higher transition frequencies. So assuming that, the frequency errors on your clock are going to be approximately the same no matter what the frequency is, if I can go to a higher transition frequency, then the relative accuracy or the relative resolution that I can get could be higher, if you can see where my cursor is down here. So approximately the precision of an oscillator goes like the frequency errors divided by the transition frequency. So the higher the transition frequency, generally the better precision. So as a result, people have been working on optical atomic clocks now for maybe 30 years or so. And they now have reached accuracies at 10 to the minus 18 and are even pushing beyond that limit. So, if we're going to talk about atomic clocks, we have to talk about the measurement essentials. And so I hope this isn't too much of a review for anybody out there, but, it's always fun to at least understand the introduction. So I'd like to talk about the differences between precision and accuracy, right? So, this is like a very standard slide to explain this, but the idea is that, if I'm going to shoot at some target, I can be accurate and I can be precise, or I can be not accurate and not precise. So not accurate and not precise is kind of this first one. So I'm not hitting the center, and there's a lot of scatter, right? Over here, in the bottom left, I'm precise, right? So I'm always hitting the same spot, but I'm not hitting the center. So I'm precise but not accurate. But what we want for standards is we want them to be both accurate and precise. So I want to be hitting the center of the target, and I want the scatter to be as little as possible. So, right, so what we're hoping for is we want a well-defined transition frequency where the errors in the definition of that frequency are very small. And so every time we measure that transition frequency, we also hope for it to be the same. And so how do we measure transition frequencies? Let's say if we're taking, because I think this is pretty important part of clocks, and it's part of what makes atomic clocks, or the second, so well defined. And so let's say I have a microwave signal from an atomic clock. So microwave signals are great because you can put them in BNC cables, and you can hook them up to handy dandy frequency counters. And these frequency counters are nice and cheap. So you can buy one of these for about $3,000 and, off the shelf get something that gives you about 12 digits in resolution in 1 second of averaging. You can play tricks with these and get up to 14 or 15 digits of resolution. You can ask me how to do that, but you might know how to do that already. And the idea is that let's say I have some unknown microwave frequency, right? From some new microwave atomic clock. What I do is I take a 10 megahertz reference, which is synthesized from, let's say, my SI second. So at NIST, we're so lucky, right? Because we have things like microwave clocks sitting around. No. But what you can do is you can synthesize microwave signals off of these at 10 hertz, plug this in the back. And what that does is it provides you a gate that is exactly 1 SI second. And then what we do is we count basically the number of zero crossings in these. And what this gives us, right, is this amazing resolution. And parts in 10 to the 12 at 1 second won't sound very exciting, but I want you to keep this in mind because I'm going to talk about this a little bit later on. Again, in terms of measuring optical frequencies. So what we do is we measure some frequency. And so talking about precision and accuracy again, in terms of what our data looks like. So unfortunately, some people do really fun AMO physics, like let's say BECs, right? And they have beautiful looking data, but clock data is very boring. And we want it to be boring by definition, right? Because what we want is we want the bottom. So, in terms of, looking at accuracy and precision again, if we look at the kinds of data that we have data at the top here, which is precise, right? There's not a lot of scatter, but it's not accurate because it's drifting, right? Or you can have something that's, accurate in the sense that it doesn't drift, but it's not precise because there's a lot of scatter. Or you have our ideal case where you have something that's both accurate and precise. So it's not drifting. So every time you measure it, it gives you the same frequency. And there's little scatter due to the fact that, you have a narrow, let's say a narrow line width or good lasers. I'm sorry, my cat is very noisy. She was sleeping for many hours and decided to wake up now. Anyways, so I want to talk also about, once again, in a different way, this idea of resolution and accuracy. So resolution is related to, in some senses, the precision. And when we measure oscillators, we measure something called an Allen deviation. This is very important for us. And so I wanted to introduce it here. So once again, we have this idea of this target, and we have this, we have this picture of this resonant frequency. And in many senses, the errors, let's say in the center frequency of this atomic transition, are related to the accuracy, right? And then the width is related to the precision. And when we look at the data that we had in the previous screen, what we do is we basically take something called an Allen deviation, and an Allen deviation is related to the standard deviation, but you're looking at it for different time frames. So, and it's a little bit different than the standard deviation because the standard deviation looks at the deviations with respect to a mean, but because oscillators sometimes can drift, what we're looking at is deviations with respect from one point to another. And so we're looking at standard deviations at different time scales. So let's say at 1 second, at 10 seconds of averaging, at 100 seconds of averaging. And what we do is we get something called an Allen deviation plot. And what it measures is the fractional measurement resolution. So this is kind of looking at how well can I define this frequency normalized by the transition frequency itself as a function of averaging time. And so we get numbers like 10 to the minus 13 or 10 to the minus 15. And what this translates to is digits of resolution. So 10 to the minus 13 gives you 13 digits of resolution and frequency, and 10 to the minus 15 gives you 15 digits of resolution and frequency. And if you're working with an atomic clock, generally you have Gaussian noise. And due to the statistics of Gaussian noise, the longer you average, the better you can define that center frequency. Does that make sense? Does anybody have questions? No? It's all good. Okay. I'm going to just let you say hi to my cat for a second since she's been so noisy. Hi, Lulu. So let's just look for a second at the historical performance of atomic clocks as a function of time. So we have these microwave talks that I spoke about. So these are the clocks that currently define the SI second. And we have our next generation optical clocks, which are the ones based on optical transition frequencies, which can achieve higher accuracies. And if we look at microwave atomic clocks, what we see is that they've bottomed out in terms of fractional accuracies, right? So this is the error on the transition frequency divided by the carrier frequency, which is about 10 gigahertz or so, right? And these have bottomed out at about 10 to the minus 16. Optical atomic clocks, on the other hand, have surpassed these for a number of reasons. One is this idea that the higher your carrier frequency, the better resolution you get. But when you can think about it a different way, and that is if I want to control a microwave transition frequency at 10 gigahertz at parts in 10 to the minus 16, I have to be able to control that transition frequency at a level of about 10 microhertz. And what that translates to is about, I have to be able to control one cycle of radiation at 10 gigahertz at 1 part in a million. So that's an incredibly challenging thing to do. So it's very, very challenging to split a cycle at 1 part in a million. And so because, they basically can't control, let's say their microwave cavities and the environment better, these microwave atomic clocks have kind of bottomed out. So they're not going to improve substantially as we go on. So this slope is stopped for the blue points. For the red points, however, because we get this additional gain in resolution due to the fact that we're working at higher transition frequencies, if I look at, let's say, 10 to the minus 18, right? 10 to the minus 18 means that I'm controlling the optical, right? And the optical transition, let's say at a petahertz, let's say, at the millihertz level. So millihertz, control at the millihertz level is significantly easier than control at the 10 microhertz level, right? And when I think about it that way, I'm only trying to control, at 10 to the minus 16, let's say, for an optical cycle, I'm only trying to control, I'm only trying to split the cycle by 1/10. So in some senses, optical atomic clocks have it easier. And so what it does in principle is that the big problem with the optical atomic clocks is lasers are difficult little beasts. So, it's easy to get them to unlock, and they have their own engineering problems associated with it. I mean, microwaves are much easier to work with in some senses than optical signals. But, if you think about it from this idea of resolution, right, because I get to operate these much higher transition frequencies, in some senses, it gives me the opportunity to kind of lessen the environmental controls on my system. And so as a result, these optical atomic clocks have reached amazing accuracies of like parts in 10 to the minus 18 now. So these are, I'm just circling some of the most recent NIST results. And the aluminum ion clock itself is, it's the scientists who operate the aluminum ion clock have pushed it down, below 1 part in 10 to the minus 18. But because, even at the 10 to the minus 18 level, one is controlling it at, 1/1000th of a cycle. There's the possibility to push beyond that. And there's the possibility to potentially miniaturize these clocks and make them portable. So I just wanted to put 10 to the minus 18 in perspective, because that's always fun, right? So we can look at it different ways. So, if you're in the US, you can think about it as being able to count the entire US budget to 1/10,000th of a penny, right? If we're looking at this target, right? Let's say we have a meter target that we're shooting at. It would be like being able to hit the center of that 1 meter wide target to within 1/1000th the diameter of the proton, right? Or, you can think about it in terms of time, as losing 1 second every 50 billion years. So because these optical atomic clocks and even microwave atomic clocks have amazing accuracies, right? And they have a host of applications associated with them. So one, you can use them to define the second. They're used in GPS. So it's kind of amazing. I think some of the first microwave atomic clocks came out in the 60s, and GPS followed very shortly in the 80s, which is amazing. And most people haven't lived their lives maybe without GPS. I have. But, and of course, timing is important in the synchronization of large networks. So, these are the, more traditional applications of timing. But, kind of these next generation applications, right, are using atomic clocks for, improved geodesic measurements. You can maybe use them for dark matter detection. I'm going to speak about that a little bit later on. And you can use them to test fundamental physics, right? Because the atomic transitions themselves are based on, our physical forces and atomic constants. So I'm going to speak about these kind of next generation applications at the end of my talk. I'm going to transition now from the kind of atomic clocks and time to frequency combs and synthesis of optical references. So I don't know if this is a good time for a break to ask questions.
It's a great time. There's a couple of questions here. So one's from Bill Phillips, and you might have discussed some of the answer, but it'd be fun to talk about. So he's referring to the cartoon version of the Allen variance. And it shows that the resolution is getting worse after the flicker floor. Doesn't the absolute accuracy keep this from rising?
Doesn't this, oh, that's a good question. Well, I guess the thing that you could say is that the flicker floor kind of defines the measure, what it's kind of a measurement of the statistics of the measurement. So oftentimes in some of our measurements, we'll have a prediction of what the accuracy of a clock might be. So let's say you have a clock and you predict that its accuracy is at 10 to the minus 18 based on the measurements that you've done. So you've gone off and you've measured your stray magnetic fields, and you've measured your stray electric fields, and you've measured the temperature of your system, right? And you've measured your collision shifts. So you have to measure, with these atomic clocks, you have to measure a million things because the atomic clocks are defined, at zero field, zero Kelvin, and at sea level, right? So you need to be able to take your operational clock, which is operating at not zero fields, right? Not zero Kelvin, and in Boulder, definitely not at sea level. And you have to be able to translate that transition frequency from the operational conditions to this ideal condition, right? And so you do all of that. You measure, how your transition frequency, shifts as a, function of applied magnetic field, let's say. And then based on all these measurements you do, you define what the accuracy is. So that now you know what the accuracy is of your temperature sensors as well, right? And so based on the uncertainties in that, you can come up with an error table, right? And you can make a prediction of your clock accuracy or uncertainty. And let's say you say it's 1 times 10 to the minus 18. And then you go off and you decide you're going to go and do a measurement. You want a reality check. So I'm going to go and measure my clock against somebody else's clock. And then what we do is we do these measurements of frequency. And so then what we do is we take these Allen deviations. So we get all these very boring looking points that are hopefully all in one line and hopefully don't have a lot of scatter. And when we take the Allen deviation, we're basically looking at this kind of like the standard deviation at different like measurement times. What we'll see is that the Allen deviation will improve as a function of time, but then we're going to hit this flicker floor, right? And the flicker floor might or might not be at 1 part in 10 to the minus 18. One, because maybe there are some uncontrolled systematics that you haven't accounted for, right? Maybe the lasers that you're using are adding additional noise. And so I don't know, Bill, if that answered your question.
Hard to get the feedback. But no, that was a very comprehensive answer. Another question here is from Dima Budker. I also have a question about the Allen plot. Could you comment on the t to the minus 1/2 versus the t to the minus 3/2 scaling?
Sure. So t to the minus 1/2 scaling in the traditional Allen variance represents white frequency noise, right? Oftentimes people will get t to the minus 3/2 scaling by using the modified Allen variance. So it's basically a different algorithm. But in the traditional Allen variance, it would be t to the minus 1/2 for white frequency noise. White phase noise, though, goes as, I think it goes as, oh yeah, white phase noise goes as 1 over root tau. I hope that answered your question.
Okay. And there's actually, we'll do one more question and then maybe let you continue to talk. So Bill Phillips asks another one, which is, how is rising sea level with global warming affecting the thinking of the time and frequency community about how to define the second?
Oh my goodness. That's a hard question. That's a very good question. I mean, I think I'm going to talk about it, but one of the big issues with atomic clocks going forward, or at least the comparison of atomic clocks, right, which is in some senses what we need to do to define the second, is that to be able to compare atomic clocks against one another, we need to know, let's say at the 10 to the minus 18 level, we need to know the relative height of the atomic clouds at the 10 centimeter level due to time dilation. So this is like a big issue, but that's a very good question in terms of, rising sea level. Where do we set sea level? I mean, I think they were doing something like this with in geodesy. They were deciding that sea level actually wasn't a good metric anymore.
I see.
But that's the big issue. So maybe from a geopotential standpoint, it would make more sense to set the, I think they're doing this with geopotential stuff. They're actually trying to set the absolute level that they're looking at in Earth's orbit somewhere.
I see.
So that was a long answer. Sorry, Bill.
Okay, no, that's interesting. Very good. So yeah, why don't you continue and we'll stop again later for some more questions.
Okay. So now we're going to talk about frequency comps. This is my area of expertise. I just want to let everybody know I am not an atomic physicist. So I'm interpreting everything. I worked with them for many, many years. And so I'm giving like the basics that I think are digestible from all of this. So, but I am a laser physicist. So this is the part I know best. Anyways, so these optical atomic clocks are amazing, right? You get these 18 digits of resolution on the transition frequency, which is phenomenal, right? But one of the big problems with optical frequencies is they oscillate so fast. So I mentioned previously the idea that, you have this nice microwave signal and it's in this BNC cable and you can plug it into a counter and you can just measure zero crossings. Wonderful to measure zero crossings on a periodic signal, right? But with optical frequencies, you can't do that, right? Because optical frequencies oscillate 100,000 times faster than your state-of-the-art computer processor, right? So you can't, put your light into an optical fiber and plug it into an optical frequency counter, right? Or can you? With optical frequency counts, you kind of can. But so that's the big issue, is that there's no electronic means to count optical signals. And so this was a big hassle at the beginning when they were developing these optical atomic clocks, because how do you connect them even to the SI second? So the SI second's at 10 gigahertz, right? But you have this gap of 100,000 between your SI second and your, right, the hertz, the definition of hertz, and this undefined optical atomic transition. And the way that they used to do this in the past, just because I feel like talking about it, and I hope I don't go too over by mentioning this, but back in the past, what they did, is I saw one of these, is that they'd take these microwave oscillators and they'd amplify them like crazy. And then they'd focus them onto these kind of nonlinear microwave things. I think of optical crystals. So definitely we're not optical crystals. But they focus these things, and what they do is they get harmonics of this microwave signal, and then so they get this higher order harmonic, and then they take a microwave oscillator, and then they lock it to that microwave signal, and then they double triple that microwave signal, and then they make it through all the domains, right? So they go from 100 megahertz to 10 gigahertz to X band to W band, whatever. They go through all the different bands, like far IR, near IR, and then they start doubling their optical signals, and then they'd have to bootstrap all of themselves all the way from microwave domain to the optical domain, and it would take many, many, many oscillators, many harmonic multiplication stages, many, many PhDs, sometimes multiple rooms, different buildings, and as a result, these systems were so complicated that they'd only do 1 to 2 measurements a year. And all that changed in the year 2000 because of the invention of the optical frequency cone. And I was in the lab. I was not working on it, but I was in the lab that was doing it. So there's all these craziness scientists running around being very excited about this mode lock laser. And I was a young grad student watching all of them thinking, well, that looks like the place that I want to work. Everybody seems very excited about that project. And so eventually that became my PhD project. Okay, so anyways, that's about me. This is not about me. So measuring a light wave. So how do you measure a light wave? So the big problem with my light waves is if you take a light wave and you put it onto a photodetector, right? If you take the voltage that comes off of that photodetector, what you're going to get is a voltage proportional to the power of the signal, right? But if I take two optical signals that are close in frequency, right, and I overlap them spatially, right? They're the same polarization, and so I basically get a beat signal between these two. If I take this beat signal, and the beat signal is at a frequency that's within the bandwidth of the photodetector, if I photodetect that, then what I get is I'll get a periodic signal at the beat frequency, or the difference frequency between those two optical signals. Well, here comes this frequency counter again. So as I mentioned previously, right? So now I have this beat signal. Beat signals are amazing because they're microwave signals. So I take this microwave signal, right? So if I take a microwave signal and I put this beat signal into my photodiode, right? I get this microwave signal and then I can put it onto this frequency counter. And I can reference my frequency counter, let's say, to the cesium fountain clock, right? So if I'm not trying to think, let's pretend this is not an optical signal right now. It's just a 100 megahertz signal, right? So if I put a 100 megahertz signal in and I have an accuracy, we're talking about accuracy here, of 10 to the minus 16, right? And then I normalize that, what I end up with is a 100 megahertz signal that I can measure with an accuracy of 10 to the minus 16. So what this tells us is, if you didn't follow the math, that wasn't complicated, but that I didn't maybe explain great, is that whatever you put in the back of this counter, if you're measuring a microwave signal, you're generally going to end up with the same accuracy. So if I reference my frequency counter to the cesium fountain clock and I measure a microwave signal, I'm going to have an accuracy of about 10 to the minus 16. But what's really exciting about optical signals is the following. So I take my optical beat signal, right? My optical signal, but I have this, let's say 100 megahertz beat signal. I take that 100 megahertz signal, I plug it into my counter. But because I get to normalize by a higher carrier frequency, what I'm doing is I'm taking these errors of the frequency counter and I get to divide by a much bigger number. And so if I'm measuring beat signals on optical frequencies, instead of being limited at 10 to the minus 16, I'm limited at 10 to the minus 23. So this handy dandy $3,000 microwave frequency counters can give me amazing accuracies in terms of measuring difference frequencies in the optical domain, which is partly what helps to facilitate impressive measurements with optical atomic clocks. And it is like the workhorse measurement system that partly helps to make time so well defined, or so well and so easy to measure. So that was like a little aside because I find that interesting. So we're going back to this idea of this frequency comb. So what is a frequency comb? A frequency comb is a laser, but it's not a single frequency laser. It's a pulse laser. And it's a special kind of pulse laser called a mode-lock laser. And what happens with a frequency comb is you have millions of modes, longitudinal modes in the cavity, and they're all coherent with one another. So they all share the same phase. So if you take a bunch of frequencies that are harmonically related to one another, and they have the same phase, right? And you add all of these together, what you end up with is a massively amplitude modulated pulse. So what I'm doing is I'm taking the energy of all these optical waves, I'm adding them together, and for the most part, you have destructive interference almost everywhere. But within, let's say, 10 femtoseconds, you have this amazing burst of optical energy. And so you have one, pulse that cycles inside of this laser cavity, and it hits a partial reflector. And what that does is it lets little copies of the pulse out. So what you have is a train of optical pulses at the exit of this mode-lock laser. And what's nice, or not nice, doesn't really matter, is that the repetition rate, right, or the periodicity between pulses related to the length of the cavity. So if I want to change the timing between pulses, all I have to do is move these mirrors around. So as I mentioned previously, right, if I take a bunch of harmonically related optical modes and I add them together, I get pulses, right? Or if I take a bunch of pulses and I take the Fourier transform, what I get is a bunch of optical modes equally separated in frequency. So this is what I would see on something like an optical spectrum analyzer if it had good enough resolution, but it doesn't, right? So these are usually the repetition rate of these lasers is like less than a gigahertz. So the spacing of these modes is less than a gigahertz. And what happens is that, let's say in the simplest scenario, is that these optical modes are each just multipliers of this repetition rate. So I have, sorry, I'm going to go back. We have a this is going to be F rep, 2F rep, 3F rep, 4F rep, and all the way up here, you're going to have like NF rep, N plus 1F rep, N plus 2F rep. But in the optical domain, N is going to be a huge number, like 500,000. But what it does is it allows me to define these optical modes with respect to a microwave frequency. And how do I get that microwave frequency? As I mentioned previously, you can't measure an optical carrier, but you can measure a beat frequency, or you can measure the amplitude modulation. And what pulses are just massively amplitude modulated optical carriers. So if I take my pulse train and I put it onto the photodetector can't detect the carrier because the carrier is too fast, but it detects the amplitude modulation. And so what I get out in terms of a voltage at the output of this photodetector are a bunch of microwave pulses with no carrier. And so now I have this optical pulse train on one side and a microwave pulse train on the other side. So if I were to take this, BNC cable with this, microwave pulse train, and I were to put it into a spectrum analyzer, right? I'd get the Fourier transform of that. And what I get is I get a decomposition of this pulse train into its, contributing harmonics. So I have F rep, 2F rep, 3F rep, 4F rep, 5F rep, up to the cutoff bandwidth of this photodetector. So why am I saying all this? So if I take a bandpass filter, I can select one single harmonic, any one of those that I want, let's say F rep. And then if I take F rep and I put it onto a frequency counter, now I know what my repetition rate frequency is. Now there's a bunch of random wires because my animation didn't work, but let's see, are things going to show up? Here we go. Let's just put all that in. So, but what's nice is that my optical spectrum lines up perfectly with harmonics of this repetition rate. So let's say I have some atomic, sample over here that's, handy, exactly lined up with one of these optical modes, right? I can define it as an integer multiplied by this repetition rate. So if I measure this repetition rate, I now know my optical frequency. So instead of, having to use multiple rooms of microwave electronics and multipliers and PhDs and, optical crystals, I need just one laser to be able to define an optical frequency. And this is also simplified. There's actually a lot of details that go into it that make it much more complicated. Like the fact that, in the end, for understanding purposes, it's good enough to think that these optical modes lie perfectly at harmonics of the repetition rate. But in the end, there's an offset. And that offset causes all sorts of problems. And it makes the technology a little bit more complicated. But even so, if you take into account the addition of an offset frequency, just makes the math uglier and it's harder to understand. You still get this kind of single step definition of optical frequencies in terms of microwave frequencies that you can measure. And these microwave frequencies are measured just using these difference frequency measurements in the optical domain. And because we're using these frequency counters, which have, let's say accuracies of 10 to the minus 16, and because we get to normalize by these optical frequencies, when we count these beat signals, the additive errors in the measurement are at the 10 to the minus 23 level. So basically, the additive optical errors are 0. So optical frequency combs essentially add no error in the measurement of atomic clocks, which is nice. So, and in addition to that, optical frequency combs can do the opposite. I don't know why my animations are all so ugly right now. Is that all of this can be turned around. So before I defined the atomic transition frequency in terms of an integer number of the repetition rate, but I can also turn this around and make the repetition rate be equal to the atomic frequency divided by the mode number that it's on. And this mode number could be measured by, taking the laser from your atomic clock and putting it into a wave meter. And the wave meter has high enough accuracy to figure out, what n it is. So we have an approximate measure of the frequency of this, and using the repetition rate, we can estimate what mode number we're on. So essentially optical frequency combs are kind of handy. They multiply and they divide. So here we're using this to divide an optical signal to the microwave domain. And the reason that we do that is that if I can measure my repetition rate, right, as the, some atomic frequency divided by n, I've now created a microwave signal that represents ticks of that atomic clock. So optical frequency combs are the clockwork that take optical signals and convert them to microwave signals that can be counted. So it is, essentially like an optical frequency counter or an optical frequency converter. And so, briefly, for these optical frequency combs, right, is, they can multiply and they can divide. So, and in addition to that, what you can do is you can use harmonic generation to go to the UV and XUV. And so if you lock an optical frequency comb to, let's say, an optical atomic clock, you can synthesize, frequencies all the way from the RF domain, like at a 10 megahertz, 100 megahertz, up to a gigahertz. You can even go to a terahertz if you try hard. You can operate in the near IR anywhere from, 4 microns or so, all the way up to 400 nanometers. And then you can do you can do harmonic generation to go all the way to the XUV. So what these do is they take this optical reference in and they can phase coherently synthesize new frequencies. So you can transfer that optical reference all across the electromagnetic spectrum. And in addition to that, because these optical frequency combs emit these pulse trains, when I stabilize the optical frequency comb, so I'm locking the optical spectrum to one of these optical atomic clocks, what happens is I also stabilize the pulse train. So I can achieve femtosecond level pulse-to-pulse timing between the pulse train, and you could use that for all sorts of interesting, like quantum control experiments for amplified pulse trains. Okay, so this is another potential stopping point. That's good. I feel like I'm gonna run far over.
Well,
I'm not on time.
Oh, we had a bunch of questions, but that's the fun part here. There's a couple more from Bill Phillips in the Q&A here. One was, the last I heard, which was some time ago, the accuracy of combs was measured to be at least 10 to the minus 19. Now that optical clocks are promising to be better than 10 to the minus 20, is the comb accuracy an issue? If there are a problem with the combs at the 10 to the minus 20 level, what could it come from?
Oh, that's a good question. So I mean, I think combs have been measured at the 10 to the minus 20 level, maybe 10 to the minus 21 level. The big problem was it just comes down to how long you want to measure. So optical frequency combs, I mean, I think the better ones in terms of 1 second instability are 1 part in 10 to the minus 18. And unfortunately, they're not 100% phase coherent. So if they were phase coherent, they would go as 1 on tau. And if they were 1 on tau, it would only take 1,000 seconds to reach an accuracy limit of 10 to the minus 21. But because there are processes that make them incoherent, so things like noise and optical fiber, what we see, because we use a lot of free space lasers, is we see that actually it's the un-Doppler canceled optical paths in the interferometers used to get beat signals against the different clocks actually add noise at the 10 to the minus 18 level at 1 second or so, a little bit higher than that. And because that process isn't coherent, it makes them average down, somewhere between 10 to the minus, somewhere between tau to the minus a half and tau to the minus 1. And so it can take up to 24 hours to reach accuracies of 10 to the minus 21. And we often don't wait long enough to go down there because the clocks aren't there yet. So we've stopped at 10 to the minus 20 because clocks are at 10 to the minus 18. But we could, but that would be the interesting question, is where's the flicker floor on these optical frequency combs?
Great. And another question is, with multiple frequencies of a comb, what about frequency pulling due to possibly asymmetric distribution of sidebands? He says, I guess when I guess that when you lock a laser to one comb tooth, that gets rid of the problem, or does it? But what about other measurements that try to focus on one comb tooth in the presence of others?
Okay, I love this because this is very funny. I learned this in grad school. What's very weird with these optical frequency combs is that if I look at the cold cavity, okay, so the cold cavity is, it's not mode locking. And the problem with the cold cavity is that there's dispersion in it, right? So I have, mirrors and they have dispersion in them. And you have glass, right? Because that's your medium. If you have a fiber laser, oh my gosh, you have lots of glass, right? And all of that adds dispersion to your cavity. And so if you look at dispersion, what that dispersion would basically say that you're not going to have longitudinal modes with the same phase. And as a result, they're not going to be equally spaced. But when you look at the mode lock laser, once the laser is no longer the cold cavity, now the laser is mode locked. If you look at the spacing between modes, you can see that the mode spacing is equal at the 10 to the minus 20 level. So what gives, right? And what happens actually in the mode lock laser is that to be able to create pulses, the contributing longitudinal modes have to be in phase. And so actually the nonlinear optics that takes place in the laser gain medium fixes the individual phase of each longitudinal mode to make it in phase. So the Kerr lens or whatever, let's say in a tie sapphire laser, fixes the phases of individual modes so they are the same. And that's what creates that's what creates an equidistant comb. And that's actually kind of magical. Like if you were going to try to do that by hand, it would be really hard. But the Kerr lens does it for you.
Oh, that's really cool. Well, in the interest of time, let's maybe proceed with the rest of the talk here.
Okay, so let's move beyond time. So I'm going to try to speed up. I was talking too slow because I'm in my kitchen and I can't see what's going on. So, for many of the kind of next generation applications of atomic clocks, you often need at least two clocks. So if I'm defining time, I kind of just need one clock. I need, let's say if it's an optical clock, I need a frequency comb to convert the optical frequencies to the microwave domain to create microwave timing signals to send away via GPS or however I want to distribute them, right? But for applications, I often need two clocks. So they can be the same species for things like geodesy, or they need to be different species for things like fundamental physics tests. So as I mentioned previously, you have these transition frequencies and they're defined based on fundamental constants and laws of physics. So if you want to do, tests of fundamental physics, you want to look at transition frequencies that have different sensitivities to either different laws or different fundamental constants. So one of the, tests that we like is to look at, let's say, time variations of the fine structure constant. And to be able to measure any time variation, you need to look at one atomic clock that has either no sensitivity to alpha, right? And then another atomic clock that has sensitivity to alpha, or one that has sensitivity in opposite directions so that you get some enhancement of the effect, right? So for, let's say, dark matter searches, we look for signals of dark matter through alpha sensitivity. And so we need two atomic clocks to be able to do that, to be able to do those measurements. So once again, frequency combs are just amazing, right? Because I mentioned that they use all these harmonically related optical frequencies, and that creates these pulses, and that's what allows you to have this connection between the optical domain and the microwave domain. But the other thing that these optical frequency combs do is because they're very broad in spectrum, right? So these optical frequency combs span about an optical octave in bandwidth. So at let's say 1.5 microns, an optical octave is 1,000 nanometers. So they span a lot of bandwidth. So if I have two optical atomic clocks with vastly different frequencies, right? I can't just take a beat signal between two clocks that are separated by hundreds of terahertz. But I can use an optical frequency comb like a ruler to be able to compare them, right? So I know the mode number of one clock over here, and I know the mode number here, and I know the spacing, right? And so I can figure out what the relative frequency difference is between the two. But unlike a ruler, so a ruler, you can take the centimeter, right? You can take the centimeter marker, and maybe you can split it by 20, right? So maybe you can resolve half a millimeter. But with the optical frequency comb, you can split a mode number, right, at parts in 10 to the 14, which is using these really wonderful frequency counters. So I can compare these atomic clocks and I can get this relative measurement of two atomic clocks versus the other. And the reason that I also want to do that is, not only for these applications, but to get past this definition of the hertz. So the definition of the hertz, which is related to the definition of the second, has an accuracy of 10 to the minus 16. But if I have an optical atomic clock that's 10 to the minus 18 or 10 to the minus 19, and I measure against the hertz, I'm going to be limited by the definition of the hertz. But if I take two optical frequencies and I take the ratio of them, the hertz disappears, right? So now I can compare atomic clocks against each other, limited by the accuracy of the atomic clocks and the frequency cone itself. So we recently had a big measurement campaign in Boulder, which we called it the Bacon collaboration for a Boulder Atomic Clock Optical Network, because we just thought that would be a great name. And what we did is we compared 3 different atomic clocks across the city of Boulder. So these clocks were one clock was located at Gilla over in Juni's lab. That's his strontium lattice clock. And then we had two clocks at NIST, the aluminum single ion clock, as well as the ytterbium 171 lattice clock. And we compared these clocks over optical fiber and also a free space link. And, we're comparing them, one, to, do some tests of fundamental physics, but we're also doing these comparisons to work towards redefining the SI unit of time in terms of optical atomic time. And one of the things that they want to see that there's consistency in these measurements, right? So to be able to claim consistency, we can't just measure two atomic clocks that are similar to one another against each other, right? So in each of these labs, they have two clocks, right? There's two strontium clocks, there's two ytterbium clocks, there's two aluminum clocks. And they do these measurements as, we talked about at the beginning with Bill's question, right? So, one species of clock will do measurements against itself and make a predicted accuracy of 10 to the minus 18. But then what we need to do is we need to have a reality check and actually, let's look at, clocks against one another and see what it looks like. And when we do that, we get our very exciting data. So we have blue, red, and yellow points. So the blue and red points are ratios using the aluminum ion clock. And the scatter in that clock is higher due to the fact that you're operating with a single ion. The two lattice clocks, so ytterbium and strontium against one another, are these yellow points. And the scatter is lower because you have 10 to the 4, 10 to the 5 atoms contributing to each of those clocks. So we have a lower quantum projection noise. And then what we do is we measure these clocks, many, many hours per day. And then we measure them over multiple days. And then we get, these very boring looking measurements where, where you have regularity in your measurements. And if we look at the Allen deviation that I talked about before, what we see is, we start with instabilities at like 10 to the minus 16. They're flat here because we're at first on the optical cavities themselves. So these atomic clocks use laser systems locked to optical Fabry-Perot cavities, which help to, pre-stabilize the frequencies of these lasers and help to narrow the line widths. And then they use those cavity stabilized lasers to probe the atomic transition. And only at about 10 seconds, 100 seconds do these lasers start to follow the atomic signal, which has this Gaussian noise, which averages down as a function of averaging time. And what we see is every day we'll get this Allen deviation, and we can use that to put statistical error bars on each measurement. And using the statistical uncertainties and then also the measured systematic uncertainties for clocks, what we can do is we can look at the ratios of these atomic clocks versus one another, and we can produce a measurement uncertainty. And I'm not going to talk about all of that too much, but because I wanted to move on to this idea very quickly of applications. So if we look at, these are individual clocks. So these are if I were to take a ratio of 1, so I go measure a ytterbium clock against a ytterbium clock, right, in the same lab, what this is showing is the accuracy of those clocks, those ratios of 1 as a function of time. Now, if I look at our clock comparisons, what we see is our current work. So it was the best, interspecies optical comparison at the time. But what we see is that these, interspecies clock comparisons aren't as good as a prediction measurement, right? And this is, very typical, right? So, if you look at yourself in the mirror, you might think you're quite beautiful. But if other people maybe they don't quite see the same thing. And so in some senses, when people are doing these measurements of their clocks in their own labs, there can be some common source, right? That, it gives the appearance of a lower accuracy. But when we do these actual clock comparisons, usually the interspecies clock comparisons are, higher by a factor of 10 or so. But I've also shown, on the right-hand side, what the relativistic sensitivity is. And so if we look at these accuracies, these fractional accuracies, at 10 to the minus 18, what we see is that the relativistic sensitivity to the gravitational redshift or time dilation means that if you have two atomic clocks that you're comparing, if we want to compare them at 10 to the minus 18, we need to know the relative height of the atomic clouds at the centimeter level. Once we go to 10 to the minus 19, we're going to have to know the relative heights between the atomic clouds at the millimeter level. And so what this does is it creates a challenge. So 10 to the minus 18, it's going to be very, very hard to compare atomic clocks to one another because, that's starting to push the limits of classical measurements with respect to Earth's geopotential. But, we're continuously faced by great opportunities, brilliantly disguised as insoluble problems, right? And so what this means is that if you're limited by something, your clock becomes a sensor, right? So in the end, these atomic clocks could potentially be used for next generation relativistic geodesy at the millimeter level, right? Also, if we compare clocks with transition frequencies that have different sensitivities to the fine structure constant, we can use these to look for dark matter detection. Should I stop? Should I whip through this? I can skip over this.
Yeah, maybe we can.
So, yeah, I want to talk about one last. So here, I'm going to skip over this for a moment. People can ask if you want, but I feel like this is kind of an important part. So in terms of applications, right, we have things like geodesy. I think June spoke about it at one point, the idea of using atomic clocks for gravitational wave detection, right? And I wanted a reality check on this, right? So if we look at the best measurements that we've done, to reach the millimeter level measurement for geodesy with two LAS clocks would take 10 months. Using the aluminum ion clock would take more than 10 years. If we are looking at gravitational waves, I think it was something like 10,000 years with traditional clocks. Partly the big problem is that we're on Earth, right? If you put atomic clocks on satellites, right, you can get outside of Earth's geopotential. Maybe you could do better and there'd be less vibration, et cetera, right? But it's a long ways away. And to conclude, I just wanted to mention one interesting thing is that when we do these clock comparisons, what we do is we have two atomic clocks and they basically operate independently. And they send the laser stabilized light to the frequency comb, and the comb kind of measures them independent of one another. But the optical frequency comb is a phase coherent system. So what I can do instead is, instead of measuring clocks kind of independent from one another, you can kind of turn the system around. So I can lock the optical frequency comb to one reference, and then I can lock a laser to one mode of the optical frequency comb, and then I can use that laser to probe a second atomic clock. And so in some senses, I can share the phase from one atomic clock with another atomic clock. This gets over two issues. One is that now they share the same oscillator. So that helps to cut down on technical noise due to the oscillator. But in systems such as the aluminum ion clock, where the probe time for that clock is limited by the oscillator, you can extend the probe time for those lasers. And for the clocks themselves, and if you extend the probe time, what that does is it improves the quantum projection noise, and you can improve the measurement sensitivity. So doing this, we recently did a measurement. So this was our previous measurement. So we're using the optical frequency comb to measure two atomic clocks kind of incoherently. If we run the two clocks, we kind of share phase between the two clocks, and then we actually synchronize the clock operation. What we saw is that we saw, basically a factor of 10 improvement in the measurement sensitivity. So if we're looking at geodesy at the millimeter level, instead of, taking 10 months, 10 years, at least with the aluminum ion clock, it would be something like 10 months. But, sorry, I don't know what's happening. Sorry. But if we were, so in this measurement that we did, we were able to improve like the probe time of the aluminum ion clock from 0.15 seconds, 150 milliseconds to 2 seconds by basically improving the oscillator that I was using. But if we were able to measure all the way out to 20 seconds, which is a maximum probe time for aluminum, it would drop the measurement sensitivity by another order of magnitude. And there we'd be able to do, geodesic measurements in less than 15 hours. And so the reason I'm mentioning this is that it's not just about the accuracies of the clocks, it's also about the resolutions in the clocks and the resolutions in the measurement. So the way that you do your measurement is important, because what that does is it decides the measurement time. And the measurement time in the end is what decides the feasibility of next generation applications. And so with that, I'd like to conclude. I'm just going to leave up this conclusion slide for those who want to read it, but it's 2:06. So I'm already over time, so I apologize.
Not at all. It was very interesting. So thank you so much for a really great talk. I'm going to maybe just ask you one question, but at the same time, encourage everybody to go to the post-seminar discussion. I think Jonathan will post the link for us. So he just did. Thank you. And there'll be lots more time for discussion and questions there offline as well. So people can feel free to ask whatever they want. So there is one question here from Dima Budker again. What is the improvement that a network of, say, 2 N clocks gives you versus just 2 clocks in these fundamental? He mentions the dark matter search. So if you had 2 times N clocks versus just 2 clocks.
Okay, so that's a good question. I'm not sure. Okay, 2, and I guess the question is are these top clocks?
Is there some kind of like square root of N improvement for the number of clocks, I guess is the question, or some kind of improvement?
Here, let me go. I'm going to go back. I'm trying to figure out how to close this. Let's go back to that. So I think it depends. I don't know if it's so much about the clock. When we were doing it, the idea is we're just looking at, here we go. We were just looking at clocks versus one another. So what really helps to improve the sensitivity in these dark matter measurements isn't the number of clocks. It's more the sensitivity of those clocks to the fine structure constant. So, if we wanted to really improve the measurement, so I'm kind of showing the measurement here, and what it's looking at is basically the idea is that with dark matter, there's I think there's many different theories for dark matter, but one of them is the idea that it's kind of like a Bose-Einstein condensate of very light, ultra light particles, and what they would do is they create a coherent signal because they'd have a wave function associated with them. And the idea would be, I'm not an expert in dark matter, so I'm saying the rightish words, but I won't be able to answer deep questions about it. But the idea would be is that the wave function, or what basically would, or this oscillation for these dark matters could be measured through the fine structure constant. And so what we would see is we'd see a periodic variation in that signal. And what we're looking at is basically a limit on the coupling strength as a function of the dark matter mass. So we're looking over like many orders of magnitude of mass. And the reason that this is sloped comes down to basically the resolution of the clocks at a given averaging time. So we have better, right? This is kind of longer averaging times. We have better resolution than at shorter averaging times. But with these, if we wanted to improve the sensitivity, either we'd improve the resolution, as I spoke about kind of recently, so we can phase coherently link clocks as a way to improve the stability in the measurement, or you can go to clocks that have higher sensitivity to the fine structure constant. So going to highly ionized ions is one way of improving sensitivity to alpha. And I know that there are some groups who are looking at those systems to improve sensitivity to this dark matter signature.
Okay, sounds good. Thank you so much for answering so many good questions and a really nice talk. And again, thanks to everyone for attending. The next seminar will be in 2 weeks. It'll be Alexandra Landsman from Ohio State, and she'll talk about photo emission from molecules, I believe. So we'll look forward to see you then. And again, check out the link for the after seminar discussion here if you'd like to join to ask some more questions. All right.
So should we go to the other link?
Yeah, so I think you can just go ahead and click on the link.
In the chat? Okay.
Can you see it? I can also email it.
Yeah, I see it. Okay. Okay, so should I just,
You can, yeah, I think it'll exit you from here and head over there. I'll come for just a minute, but I do have to run away. Right
okay.
Now. Same.
Okay.
I'll hang out here just
okay, thanks, John.
So the thing stays open if people want to click the link.
Okay, leave.
And that's it.